So I'm Tom McClelland from Frequency Electronics. We're in the business of precision, time, and frequency. I'll tell you a little bit about FEI, as we're known, over the next couple of minutes. So just a brief introduction. We've been around for 55 years, quite a while. We're a small business. We produce quartz and rubidium precision, time, and frequency devices. We like to think of our specialty as taking technology from the laboratory, things that are demonstrated in the laboratory, and making practical products that can be used in the field, primarily in military and space applications. We have a lot of technical expertise in-house and a pretty robust R&D program internally, and that's what feeds the product development. A snapshot of the company. Many people probably haven't heard of Frequency Electronics, but we were founded in 1961. So we've been around for a while. We have about 150 employees. That qualifies us by government definitions as a small business, but it's a little bit more than a garage shop with just 1 or 2 employees. We have 100,000 square feet of laboratory space at our main facility on Long Island, and we have a couple of subsidiaries, one in California and one in New Jersey. We have, for fiscal year 2020, our last fiscal year, we had revenues of $41.5 million. So we like to think of ourselves, an important aspect of the way we do business is we're a vertically integrated company that we feel is very important for the type of technology that we deal in. As John introduced, it's precision clocks, and it's very, in order to get the kind of performance that people are looking for in these things, everything needs to be done correctly. So it's important to have a lot of control over the raw material, from the raw materials to the finished product. So we for the technologies that we deal in, we try to control as much as we possibly can. So for instance, quartz oscillators, we manufacture the quartz resonators in our own facility. We control all of the processing, and we finish with quartz oscillators that go into larger systems. For rubidium atomic clocks, we start with literally with isotopes of rubidium, and we produce all of the cells, the vapor cells that those go into, and the finished atomic clocks. So the next couple of slides, I'd like to sort of walk through FEI's history. And the starting is not the first thing that FEI did, but it's kind of a key thing. Back in 1977, we manufactured quartz oscillators for the Voyager spacecraft, which were actually launched in 1977. And they're still out there working at this point in time. The quartz oscillator that we manufactured for Voyager 1 stopped operating a few years ago, but it had a lifetime of 34 years in space, and the Voyager 2 quartz oscillator continues to function to this day, so it's over 40 years at this point in time. So that kind of gives a little bit of flavor to the kind of reliability that can be had from these things, and how long FEI has been contributing. The next thing, we're going to flash forward from 1977 to 2013, pretty close to the present by comparison, and we're just showing contributions that we made to the Iridium Next satellite system. And the thing we want to emphasize here is it's for a space system. This is relatively large quantity. So the Voyager satellite, we produced 2 oscillators, In this case, we produced a whole lot of devices. The Iridium system is a satellite constellation of 66 active low Earth orbit satellites. So some of the parts that we did for this, we had over 2,500 assemblies that needed to be manufactured. So we go from a very custom, one-off kind of production to a relatively large manufacturing capability. Going on to 2014, a year later, we delivered to the Jet Propulsion Laboratory ultra-stable quartz oscillators that are used as a key part of the deep space atomic clock, which just got launched and actually is still operating in orbit at this point in time. These oscillators produce pretty much state-of-the-art performance in terms of Allen deviation. For quartz oscillators, we're down in the 10 to the 14 range at averaging times of about 10 seconds. We move on next to 2015, and we developed at that point in time what we call a digital rubidium atomic frequency standard. This is developed for the GPS satellite system. This is a very high precision vapor cell rubidium atomic clock. We introduced some digital control electronics for this device. And this is just starting to come online right now. Literally within the next couple of days, we should be starting qualification testing of the qual model for this unit. And now we move on to the current time and technology that's under development at FEI. This one we're kind of proud of, the so-called pulsed optically pumped, or POP, rubidium vapor atomic clock. And this is still a vapor cell atomic clock, but by using a pulsed laser as a light source, we can get roughly an order of magnitude improvement in performance. So this is still a vapor cell clock, and as John Kitching stated, this has limited stability capabilities. But the key nice thing about that is it's a proven technology that's been fielded. There are thousands of vapor cell atomic clocks out there. So by making a very small change to the design of this, we can get a big improvement in the performance. So this is kind of a middle ground of a very high performance atomic clock, but we know that we can make it in small packaging, in vibration resistant packages, etc., that are ideal for a lot of applications that people are looking for at this point in time. We're also working directly with the Jet Propulsion Laboratory to actually manufacture in volume their Mercury Ion atomic clock. We talked a few slides back about the deep space atomic clock. That's a Mercury Ion clock, and we are actively working at this point in time to bring that technology, to manufacture that technology. This is kind of a step beyond the pulsed optically pumped vapor cell clock, because it's stored ions that are isolated very well from the environment. We expect much better long-term stability from this kind of technology. And finally, we looking to the future, we're actively working on clock ensembling. The idea here is that we instead of trying to make one better clock, we combine the performance from multiple clocks in order to get a better measure of time and frequency. We're also looking toward advanced optical atomic clocks, as John kind of described in his presentation. We have a lot of interest in photonic oscillators that primarily looking at improved phase noise. And we're also interested in quantum computing. So finally, that's about it. The last slide just gives some context if anybody is interested in working with us in any way. Here's how to get a hold of us.